Next example is find a particular solution of y double prime minus 3y prime minus 4y is equal to 2 sin t. Here Rx is 2 sin t. From this we have to guess what our candidate for particular solution will be, or we want to apply undetermined coefficient. So is it a sin t, which is very similar to Rx? No. Remember that whenever Rx is either sin t or cos t, a linear combination of sin t and cos t should appear as a candidate for the particular solution. So here yt is a sin t plus b cos t. This is a candidate for the particular solution. So the derivative of y is a cos t minus b sin t. Double derivative will be minus a sin t minus b cos t. So when you substitute this in the given nonlinear ODE and collect the coefficients of sin t and cos t, this is what we get. We have to transfer the 2 sin t on the left hand side, and we have to substitute all this y double prime, y prime and y in this equation. This is what we get. So we equate the coefficient of sin t to 0 and we equate the coefficient of cos t to 0. Why do we equate that? You can pause the video and try to answer the question. That is because sin t and cos t are linearly independent. When we solve this system of linear equations, we get a to be equal to minus 5 by 17 and b to be equal to 3 by 17. We substitute these values of a and b back in this candidate for particular solution. So we get yt is equal to minus 5 by 17 sin t plus 3 by 17 cos t. Our next example is find a particular solution of y double prime minus 3y prime minus 4y is equal to 4t square minus 1. So what will be the candidate for the particular solution? Recall from that slide that I had displayed. When here we have a polynomial of degree 2, then the candidate solution is going to be an arbitrary polynomial of degree 2. So here the candidate solution is at square plus bt plus c, where a, b and c are all arbitrary constants which we have to determine by undetermined coefficient method. So we calculate y prime, y double prime, and then we substitute y double prime and y prime in this equation. This is what we get. So we collect the coefficient of p square and equate it to 0. We collect the coefficient of t and equate it to 0. And we collect the constants and equate it to 0. Then we solve this system of equations and we get a is equal to minus 1, b is equal to 3 by 2 and c is equal to 11 by 8. When we substitute this back in this candidate for our particular solution, we get yt is equal to minus t square. We substitute a is equal to minus 1. So yt is equal to minus t square plus 3 by 2t minus 11 by 8. We substitute the value of b and c from here to get this particular solution. The next example is find a particular solution of y double prime minus 3y prime minus 4y is equal to minus 8 e raised to t cos 2t. Looking at the Rx, we decide that the candidate for particular solution will be yt is equal to a e raised to t cos 2t plus b e raised to t sin 2t. Note that, as before, if in Rt a constant multiple of e raised to alpha t cos beta t appears, then the candidate of particular solution will be a linear combination of e raised to alpha t cos beta t and e raised to alpha t sin beta t. So in this case, the candidate for particular solution is yt is equal to a e raised to t cos 2t plus b e raised to t sin 2t. Y prime t is equal to a plus 2b bracket close e raised to t cos 2t plus in bracket minus 2a plus b bracket close e raised to t sin 2t. You can easily check this is the derivative of the y that is given here. Then we compute y double derivative. You can again verify that the double derivative expression will be bracket minus 3a plus 4b bracket close e raised to t cos 2t plus in bracket minus 4a minus 3b bracket close e raised to t sin 2t. When you substitute this y double prime, y prime and y in the given equation and collect the coefficient of e raised to t cos 2t and equate it to 0 and collect the coefficient of e raised to t sin 2t and equate it to 0, then we get these two equations. So they form a system of linear equations. When you solve this system of linear equations, we get the value of a and b. Substitute the value of a and b in this expression for particular solution. So we get yt is equal to 10 by 13 e raised to t cos 2t plus 2 by 13 e raised to t sin 2t. Our next example is find a particular solution of y double prime plus 4y is equal to 3 cos 2t. Since the Rt here is equal to 3 cos 2t, we should look for solutions of the form yt is equal to a cos 2t plus b sin 2t. Thus, y prime t is equal to minus 2a sin 2t plus 2b cos 2t and y double prime is minus 4a cos 2t minus 4b sin 2t. Substituting in the differential equation, we get this expression. So what you have done is y double prime this expression and y prime this expression and y is this expression you have substituted in this equation. We get the left hand side to be equal to 0, whereas the right hand side is not equal to 0. So we are not able to determine the values of a and b. So undetermined coefficient method is not working. Can you guess what is the reason? The reason is that sin 2t and cos 2t are also solutions of the associated homogeneous ODE y double prime plus 4y is equal to 0. See, that would be the homogeneous ODE or this non-homogeneous ODE. So we know that whenever such thing happens, we have to modify our proposed solution. Why this happens? That is because for the characteristic equation m square plus 4 equal to 0, 2i is a root. Which gives rise to sin 2t and cos 2t being solution of the homogeneous differential equation, but that is similar to the RT here. So we modify the proposed solution by multiplying cos 2t by t multiplying sin 2t by t and taking the linear combination. This is what was explained to you in that slide where it gave you a general scheme for finding the candidate for particular solution. So I am referring to this slide. So whenever such thing happens, we multiply by x raised to the multiplicity of the complex root of the characteristic polynomial. In our question, 2i has multiplicity 1.
And in our case, the independent variable is t. So t raised to 1 should get multiplied to a cos 2t plus b sin 2t. So we have here the modified proposed solution as yt is equal to at cos 2t plus bt sin 2t. So the y prime t is equal to b minus 2at, this thing in bracket, multiplied to sin 2t plus bracket a plus 2bt bracket close cos 2t. Then we compute the double derivative. So y double prime t is equal to minus 4at cos 2t minus 4bt sin 2t minus 4a sin 2t plus 4b cos 2t. We substitute y double prime, y prime and y in the given differential equation, and substituting we get this form. So we collect the coefficient of sin 2t and equate it to 0, and we collect the coefficient of cos 2t and equate it to 0. From that we can compute a and b. You can compute yourself and you can verify that the value of a comes out to be 0 and value of b comes out to be 3 by 4. And so the particular solution in this case is yt is equal to 3 by 4 t sin 2t. This we have obtained by substituting the value of a equal to 0 and b is equal to 3 by 4 in this equation. Next we consider the case when the Rx consists of terms R1, R2, R3 up to Rn, where each of them is to be dealt with separately. That is Rix or e raised to ax or sin ax or cos ax or polynomial in x. They are of different types, so we handle them separately. So we consider n subproblems of the second order ODE, namely y double prime plus p y prime plus qy is equal to Rix. If y1 is a particular solution of this problem, then a particular solution of the second order non-homogeneous ODE is ypx is equal to y1x plus y2x plus dot 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 ynx. We'll see an example illustrating this method. So here you see we have been asked to find the particular solution of y double prime minus 3y prime minus 4y is equal to 3 e raised to 2t plus 2 sin t plus 4 t square minus 1 minus 8 et cos 2t. So here I can treat this as r1x, this as r2x, these two terms together as r3x, and this one as r4x, because they are all of different types. So Rx consists of these four terms. We need to solve each of them. That is, we have to solve R double y double prime minus 3y prime minus 4y is equal to RIT. And for each of this, we get a solution y1t. And then the final solution yt is given by y1t plus y2t plus y3t plus y4t. Each yit is a particular solution of this kind of ordinary differential equation. So we can see that this equation with 3e2t already appeared, and the particular solution for this here is of this form, minus half e raised to 2x. So in our case, minus half e raised to 2t. So we use that. Minus half e raised to 2t. Similarly, the term 2 sin t also appeared in the previous slides. Here, and the particular solution minus 5 by 17 sin t plus 3 by 17 cos t, we use it. Here, the term 4t square minus 1 appeared. Here, and we take this solution minus t square plus 3 by 2t minus 11 by 8, and we write it here. And the last term minus 8 et cos 2t appeared here, and we have 10 by 13 et cos 2t plus 2 by 13 et sin 2t as a particular solution, and we use it here. By adding those 4 particular solutions, we got the particular solution of this second order ODE. One more remark about the method that we need to employ for undetermined coefficient. Instead of this particular scheme that has been illustrated, the second one, when the Rx is of the type x raised to d e raised to ax cos bx, or x raised to d e raised to ax sin bx of the type, sometimes it becomes very complicated using this particular method. So we can use another method. This method will be shorter in some cases. So this method says, let A be a complex number and PD yx equal to Rx be a linear differential equation. So we are writing the differential equation using this notation. This is a polynomial P with the variable, the differential operator d by dx. If the Rx, the right hand side, is equal to x raised to d e raised to ax, or even px e raised to ax, with px being polynomial of degree t, then the candidate solution is yx is equal to x raised to mu a qx e raised to ax, where mu a is equal to the number of times a occurs as a characteristic root. Qx is a polynomial of degree t. So here qx is ad plus ad minus 1x plus dot 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 a naught x raised to d. So here ad minus 1 and so on up to a naught are undetermined coefficients which we have to determine by substituting this candidate for particular solution in the differential equation. And while solving this, a useful fact is PD applied to e raised to ax fx is equal to e raised to ax p d plus a fx.